like I said, in this video, I want to kind of go over the examples I previously went through on a software that I'm gonna use R for my examples for my videos, just because that's the way I learned in class. So I won't go through. Obviously, I won't go through all the examples. In fact, majority of the concepts that I went through, I'm probably not gonna get through it. But I did want to demonstrate some examples that I think are not only important but a little easier to kind of demonstrate it in R. Okay, so a while back I mentioned the discrete random variable example of a dice roll. So if we make an object for that, so given the values 1 through 6 of a dice roll, we can find the simple statistics that we measured from a dice roll, like the variance and the standard deviation, just by simple commands. So if you run that, okay, so variance, like I said, is 3.5, and then the square root of it is the standard deviation. And then for our covariance and correlation, obviously we can't do the dice roll. We need to create the two other vectors that we created before. In this case, our hours of sleep and the grades in result. For these are the exact numbers I used in my on my blackboard. Okay, so if we give the sleep and grade objects for those, then we can simply just measure the covariance and correlation just by giving the COV function and then putting the two objects in. So 18, and then 18 is our covariance, and then correlation is, again, 1, very close to 1. I think it's important to note that oftentimes we're not too concerned with, well, we are concerned with finding the covariance and correlation of such things, but we're often going to have to do it in like some sort of matrix or data set that we don't visibly see on our notebook or markdown or whatever. So usually when we try to filter out a factor of like a vector of these sorts, we want to give the name of our data set, and then we want to put the $, and then the name of the factor or vector, in this case like grade, or sleep or whatnot. Okay, so there's that. So now let's try to so I want to go over the central limit theorem now. Central limit theorem, let's just name these. So stat. Okay, central limit theorem. I don't know why I deleted that. Okay, so for the central limit theorem, recall that as the sample size increases, the distribution of any random variable that has like a given mean and a SD, it will become closer to a normal distribution, right? And the easiest way to demonstrate that on R is by a histogram, by creating like a random normal distribution of a histogram, or creating a histogram of a random normal distribution. So Hist is the function for the histogram, R norm, random normal distribution. And then simply the arguments for the normal distribution, we can see that we can give as like the sample size of 10. We'll give it a small sample size, and then we'll give it a standard normal distribution. Okay, so standard normal distribution of a mu of 0 and an SD of 1, sample size of 10, we're creating a histogram for that normal distribution. Okay, so if we get our output, it'll look something like this. And again, because our sample size is so small, it does not look like a normal distribution at all. And then we can actually continually output this function like repeatedly, just because the R norm, it creates a random normal distribution every time you call for the output. So again, well, that one kind of looks like a normal distribution, but most of these, they don't, the sample size is too small for us to get a reliable normal distribution. So let's instead of a sample size of 10, let's give it like 30. And then if we get the output here, okay, well, some of these, again, look like a normal distribution. That one is close. That one, not really. So clearly our sample size of 30 in this case isn't large enough to consistently get a normal distribution. Okay. So from trial and error, I kind of figured out that 500 will pretty much give a standard normal distribution. So most of these kind of look like the highest frequency is around the mean, and then as we stray away from the as we stray away from the mean, the frequency significantly decreases. Okay, so now that we've done that, I want to do confidence intervals. So let's give this function a name. We'll just call it our standard data. Okay. Okay, so we'll call that standard data, and then when we want to create confidence intervals, we often do some sort of testing, which is what confidence intervals are actually used for. But obviously I haven't gone over that yet, so I won't go over like the p-value and all that stuff, not just yet, but let's just do a t-test of the standard data for now, and then we can give our confidence interval to a 90%. All right, so, and then again, we already gave our mean and our standard deviation and our sample size, so all we need to give is our confidence interval when we're testing out this function. So if we output that, says variable in x is not true. Did I spell confidence wrong? Okay. Okay, so I did realize my mistake in that I can't do a t-test of a histogram, obviously. So I didn't make an object here. All I did was call the function, and then I made an object for the standard data of a normal distribution, not a histogram of it. So that was my mistake. And so if I do a t-test of the standard normal distribution with the confidence level of 0.9, even before looking at the result, I can tell that my confidence interval will be really low because my standard deviation is low and then my sample size is high. So these the 90% confidence will be given around right here. So negative 0.02 to 0.12. Because it's a normal distribution, and I could get a new one every time I recall it. If I like output it again, I will get like a different confidence interval. But generally, they should all be pretty low. And so what we could do is we could actually manipulate this standard data characteristics. So let's say I decrease the sample size and then also increase the standard deviation a bit. If I do that, then our confidence interval will become higher because we manipulated all the changes of what makes our confidence interval increase, since we've made our data less reliable by decreasing the sample size and having a bigger spread. Even if we increase our confidence level, let's see what we get from there. Right, so our confidence interval significantly increased because we well, actually, I guess increasing the confidence level doesn't decrease the interval. So using the same 90%, our confidence interval still significantly increased because we have a much smaller sample size, as well as the spread of our data, or our standard deviation or variance or sample error. They're all similar in a way where we get the spread of the data. That part of our data increases. So that's nice to know on how our confidence interval is determined by those factors. This p-value, t-value right here, I did mention t-value, so I guess you can take a look at that. But our alternative hypothesis, p-value, and all that stuff, I'm going to go over the future videos on linear regression, which is what the series I'm covering next. So we don't have to worry too much about that for now, but it says our mean and then our confidence interval is what we're mostly concerned about. But yeah, those are just the three concepts I wanted to go over in this video. And in my next video, I'm gonna start a new series. I'll most likely resume the mathematical statistics later, just because I want to go into the linear regression type of stuff. But for now, I'm done with covering the mathematical statistics.